Hello, welcome to online webinar by Photoneo, Introduction to BIM Picking Studio. My name is František Takac and I'm Strategic Partners Manager here in Photoneo. Today, with my colleague Patrick Bakita, BIM Picking Studio Product Specialist, we are going to present you the ultimate robotic intelligence, BIM Picking Studio. Photoneo is a leading provider of industrial 3D vision, AI-powered automation solutions, and robot intelligence software. Since the foundation in 2013, the company's mission was to give vision and intelligence to robots all over the world so they can see and understand with a clear goal: to automate monotonous and risky tasks by employing vision-guided robotics. We have delivered over 3,000 solutions worldwide, and our technology was recognized by the highest honors, including the Vision Award in 2018 and Platinum Innovators in 2019. We have headquarters in Central Europe, Slovakia, with branches in USA, Kentucky, and China, Shanghai. Globally, we employ more than 200 people, and we cooperate with more than 50 distributors, which can provide you with sales and technical support. Why we have started with BIM picking as the first problematics in vision-guided robotics? I'm sure you saw this kind of production line or participated on its build. And it's surely an amazing piece of technology. So, at one side, you have metal plates which enters the process of manufacturing, and there is a number of welding robots, and on the other side of the production line, every minute or so, there is entire car chassis built. Now, while this looks amazing, there is one problem associated, which was also a cost. If you want to put anything into this production line, it costs you money. Either it is operators stacking the metal sheets at entry level of the production line for the robots, so they can go to exactly same position for every cycle, or you need to build or buy one-purpose machine, or the construction of stacking these metal sheets, pillars, screws, or anything required for a car chassis to be built. In Photoneo, we were thinking about if there is anything we can do about it, and solution of that problem already exists for a couple of decades, and it is a subject of research of vision-guided robotics. The definition of vision-guided robotics is simple: a robot that should be equipped with a sensor or camera, and if you do so, your robot should be able, with the involvement of certain vision algorithms, to move towards this target. The growing need for smart automation has caused that 3D vision, as an integral part of vision-guided robotics, has continuously been expanding into new markets. Gradually, the 3D vision has entered application areas such as robot guidance, BIM picking, advanced object handling, depalletization, path correction, assembly, quality control, inspection, or shape evaluation. Photoneo has the capability to solve this application with in-house developed hardware and software, offering customers the most complete solution for the most advanced task requiring 3D vision. In general, it is easy to program robots to repeat certain movements. It requires putting a part to the same position every time. However, sometimes it is cumbersome to create purely mechanical system that fulfills the requirement. Therefore, most of the tasks are performed by human operators. Foxy 3D vision systems provides robots with sight and understanding, so they are able to adjust their movement while handling parts placed randomly, and there is no need for the mechanism ensuring specifically set positions of the parts being handled. Our motivation is transforming experience and knowledge from projects delivered by Photoneo into a product which enables our partners to deploy robust and reliable BIM picking applications. With BIM Picking Studio, we are able to adapt to many scenarios regarding 3D vision guided robotics picking. Either it is parsed, placed in the bin in the structured way, in a semi-structured way, or completely randomly oriented objects. Why bin picking? In Photoneo, we have started to work on bin picking application because this is a core problem in computer vision and robotics. The goal is to have a robot with sensors and cameras attached to it and pick up known objects with random poses out of a bin using suction gripper, barrel gripper, or another kind of robot end effector. So, why is it difficult to do bin picking? If you think of it, it was not so many years ago when the majority of the bin picking applications were actually built on greenfield. What you need to do as a company, you need to acquire certain skills in order to build a bin picking applications. So you definitely need to have a person who understands mathematics, geometry, robot kinematics. You need a person who is able to work with technical drawings, a person who is capable to program a robot, and you need the operating system for running your software. You need to have a solid software engineers to implement vision algorithms. You need to have a 3D vision sensor or camera, and you need to be able to create localization algorithms. This is a wide variety of advanced skills, and it is really difficult to find a person which master all of these skills. And even if you find somebody, it would be a very expensive thing. If you want to build a team where each member master one of these skills, it's not going to be cheaper either. So, we at Photoneo, we were thinking if there is anything we can do about it, and we found out there are actually just two skills which are available in the area of our customers, and it is a technical drawing and robot programming. So, we created a tool which is designed for robotic integrators. When we look at the Photoneo product portfolio, the entry-level product is a Foxy 3D scanner. This is your go-to scanner when looking for a high resolution and a high accuracy scanning of static scenes. Its structured light projection approach provides output in the form of precise point clouds for fast localization of any desired part. The robustness of the scanner ensures superior quality of scans, which makes it best scanner for even the harshest environments. Foxy 3D scanner was awarded by the Vision Systems Design Innovators Awards program for its unbeatable performance and best-in-class resolution-to-speed ratio. Photoneo Motion Cam 3D is the world's highest resolution and highest accuracy area 3D camera for dynamic scenes. It is your go-to device for applications requiring fast and robust 3D acquisition. You can reconstruct accurate point clouds of various objects in a high level of detail without compromises on quality caused by vibrations, ambient light, or motion blur. This makes it your ideal 3D vision companion for handling objects in motion. The bin picking studio solution is well established on the market, and we're currently offering its version 1.6. This is a complete solution which consists of sensor, superior 3D vision with various sizes and scanning ranges, as well as optimized features for bin picking. It is also equipped with localization, an in-house developed CAD-based localization algorithm with smart features for bin picking like smart memory and quick scan. Solution is featured with full path planning and collision avoidance. Path planning is optimized for 6-axis robotic manipulators with an option of disabling the collision check for the speed boost in collision-free environments. Also available with a plugin for your robot of your choice is a generic interface to a wide portfolio of robots, 11 different robot brands, more than 200 support robotic models, and also offering a wide variety of commands. Photoneo is offering multiple localization approaches for different industrial areas, such as general industry, machine tending, plastic industry, foundry, logistic industry, and parcel handling or apparel industry. We were thinking how to create a topology of such an application. If you buy an industrial robot, you already in default configuration have a pretty nice specification. However, since the robotic applications are very wide, you can still buy an option to extend the capabilities of a robot. This could be I/O cards, safety options, conveyor belt tracking, or anything you can think of. We have built our software to be a complementary third-party option to the already available robotic options. So how does it really work? You are getting an industrial-grade PC, which have a direct connection to the Photoneo Foxy 3D scanner or other sensor, and this industrial PC has a direct connection to the robotic controller as well. We do not change the working habits of the robotic programmers. We are just trying to extend the capabilities of the robot they are using. With our software and hardware configuration, you are getting also a plugin, which is a set of functions for your robot. So you just get a USB key and you upload the additional plugin to the robotic controller, and suddenly you are able to call a new set of functions. One could be trigger scan or request for the trajectory, request for the localization, and many others. So it is very natural for somebody who have experience working with a robot to adopt our technology because it is very compatible with work and topology of the robotic controller. We are working in the topology of client-server application, so we act as a server and we are serving the request from the robotic controller, so the flow of the program is still fully enhanced, and we work around any safety functions or doing anything unusual.
Thank you, František, for the introduction. My name is Patrik Bakita, and I'm the Beam Picking Studio product engineer. Today, I'm going to present to you the key features of the Beam Picking Studio. Afterwards, I'm going to configure a new beam picking application and demonstrate beam picking with the help of the Kawasaki robot. Let's begin. The beam picking system you receive from Photoneo consists of several key components. The first part is the vision system, the eyes of the application. This is either the Foxy 3D scanner or the MotionCam 3D. In the majority of cases, the sensor to use is the scanner, although the MotionCam has its own advantages that can be utilized in some special applications. The second part of the system is the localization engine. It takes the input from the vision system, the acquired point cloud, and searches in it for the objects of interest. The localized targets are then passed to the path planning pipeline, where they are sorted and the system generates collision-free trajectories for the robot to be able to pick them. The last component is the communication interface between the beam picking system and the robot. Once the beam picking system comes up with a suitable trajectory, it can pass it to the robot to execute it and pick the object. All these components are delivered to you in a single package containing the vision sensor and the vision controller, an industrial-grade PC with pre-installed Beam Picking Studio. You just need a robot and a gripper suitable for your application. Regarding object localization, Beam Picking Studio offers two types of localization engines. The first one is analytical. It takes the point cloud from the vision sensor and the CAD model of the object to be localized and applies analytical methods to find it in the point cloud. This approach is suitable for objects that do not vary in shape and size. The second engine is based on machine learning. It uses a neural network to identify objects of interest and suitable surfaces where the gripper could grasp the object. Therefore, the objects do not need to be identical. The neural network can learn to recognize all kinds of objects of various shapes and sizes. The robot model defines the kinematics of the manipulator, which is essential for path planning, and it is also used for real-time visualization. Beam Picking Studio supports almost 200 robot models of several robotic brands. All these models are a part of the system and ready to be used. In case your robot model is missing, it can be easily added to the robot database upon request. There are two options available when it comes to placement of the vision sensor. You can either put it in a static position above the bin, or you can attach it directly to the robotic manipulator behind the last joint. Both approaches have their advantages. For example, with the static scanner, the robot's maneuverability is not limited and it does not have to stay still during the scan acquisition. On the other hand, the hand-eye approach enables capturing the scene from different viewpoints, getting closer to the objects and thus getting a more detailed point cloud, which improves localization performance. The objects are localized in the sensor's coordinate system and the robot needs them in the coordinate system of its own. Calibration is the process of identifying this transformation between the sensor's camera unit and the robot base. The process is very simple, performed using one of the provided calibration tools based on the calibration type, extrinsic or hand-eye. The calibration can be executed by the robot itself. Photoneo provides a program template that only needs to be added the calibration poses of the robot. Once prepared, you can execute the calibration anytime needed in a matter of minutes. Bin Picking Studio has a user-friendly and intuitive graphical interface. Very little skill is needed to operate it. All you need to know is the basics of CAD. CAD files define the gripper of the robot, the objects you want to localize, and the collision objects in the environment. Bin Picking Studio also contains a tool for drawing simple collision objects directly inside it. Often, you need to work with multiple objects in a single bin picking application. The full configuration of your application is defined in the bin picking solution, which is divided into vision systems. A vision system is a concept that ties together several things: the physical sensor used by that vision system, the calibration for that sensor, because each vision system can use a different sensor, but also all of them can use the same one. Then the object to be picked by the vision system, and the localization profile which holds the parameters for localization of that object. The grasping method defining the strategy for object extraction, and some settings unique for each vision system. A bin picking solution can use up to 4 vision systems, which means you can work with 4 different objects in a single bin picking application. The main goal of the Bin Picking Studio is to find collision-free trajectories for the robot to safely navigate it to the localized object so it can extract it from the bin. Since the objects are placed randomly in the bin, every single trajectory is unique and a result of complex mathematical computations. To avoid any chance of collision, all elements in the scene are considered collision objects, including the point cloud from the sensor and the robot itself. Based on the bin picking application and its requirements, there are a couple of path planning modes available. For the simplest environments with no obstacles and shallow bins with no risk of collision, there is an option to turn off the path planning and collision avoidance feature. Or you might keep it just for segments of the trajectory that are around the localized object. This approach will lead to very low computation times and thus fast cycle times. On the other hand, in a complex environment with obstacles and deep bins that the manipulator needs to reach into, path planning and collision avoidance should be turned on. The path planner will find a way around all obstacles and safely navigate the robot to the object inside the bin. After the object is picked, the path planner takes it into account when planning the trajectory back out of the bin in order for the picked object not to collide with the walls of the bin. While commissioning the bin picking application, you might need to tweak some parameters to achieve the best results. To simplify and speed up the testing phase, the Bin Picking Studio includes the first iteration of its simulation feature that enables you to test the basic bin picking functionality without the use of the real robot. During the run of the bin picking application, whether that is in the simulation or production mode, Bin Picking Studio renders the localized objects with different colors based on their path planning status. Moreover, it offers a powerful debugging tool that lets you inspect any localized object, check all its properties, and preview the computed trajectories. For the trajectories and other segments of the path plan that fail to be computed, it provides the reason for failure. In the animation, you can see that the red object cannot be picked right now from any direction because the gripper would collide with the wall of the bin. On the other hand, Any green object is a suitable candidate for picking, and you can preview its complete trajectory. The last thing I would like to talk about for a bit before we move to the bin picking studio itself is the remote access feature. When the bin picking application is deployed into production in your factory, it is beneficial to be able to check its status anytime needed. Bin picking studio lets you do this remotely using one of the available remote access methods. The first one is access from the web browser of your own computer. Bin picking studio is a web-based application that runs locally on the Vision controller, but can also be configured to be accessible from other devices on the same local network. The other option is the use of the pre-configured VNC server running on the Vision controller. You just need a VNC client of your preference installed on your own computer that lets you connect to the server on the Vision controller. The last option is to use the pre-installed TeamViewer. This application is mostly used by Photoneo support technicians when providing remote support. Okay, that's it from the presentation. Let's go directly to the bin picking studio. Bin picking studio is running on an industrial-grade PC that we call the Vision controller. The operating system is Ubuntu 18. All bin picking studio related stuff is located on the desktop. So there are some example solutions that you can import into the bin picking studio and check them out. There is a directory where you can put your saved scans to create fake scanners out of them for later use when you do not have the real scanner connected. And there's also a directory where you can save the scans. Bin picking studio is started automatically when the Vision controller boots up, but it can be also started, restarted, or stopped using one of these shortcuts on the desktop. During the whole time the bin picking studio is running, the Foxy control is running too alongside it. The Foxy control is the application that is used to operate the scanner. You would use it to configure the advanced parameters for scanning. So let's go to the bin picking studio. This is the login page of the bin picking studio. I'm going to log in into my account that I created when I first started my bin picking studio. And now we are on the main page of the bin picking studio, on the solution page. The solutions page consists of the list of available solutions of your bin picking projects. You can duplicate an existing solution, you can delete it, export it, or import from backup, or of course you can create a new one. But before that, let's check what else is there. There's the deployment page. Here you can choose your fully configured bin picking solution and deploy it. Then there's the Foxy interface. This is just a simple interface for Foxy control for testing of basic scanning parameters and for downloading scans. For adjustment of advanced parameters, you should always use the mentioned Foxy control. And then there's the network page, which serves for configuration of communication interfaces. For the communication with the robot, we have the robot interface here. So this is the IP address of the Vision controller, and the robot controller IP address is right below it. For communication with the scanner, we set up either DHCP server or a static IP on the scanner interface. Scanners can be pre-configured with DHCP client, so the DHCP server is the initial option, but we recommend setting a static IP on both devices. For setting up the static IP on the scanner, you would use the Foxy control. And finally, there's the network interface. Leave it on the DHCP client option if you are on a network with a DHCP server, or you can set up a static IP. You would use this interface for connection to the internet and for remote access to the Vision controller. In the menu in the corner are other options: user profile, account management, documentation, and option to download logs for diagnostics. Okay, let's get back to the solutions page and create a new one. On the left side, I have the solution wizard with several sections that need to be completed in order to fully configure the solution. You can see that right now Basically, all of them have gray check mark, which means these steps are not yet completed. And when they are completed, they have the green check mark. Let's name our solution. I'm going to call it beam picking demo. It has an ID which has been pre-generated, but I can give it a one of my own preference, so for example 10. Through this ID, the robot can request the solution to be deployed, so this is an important value. I can give it some description if needed, and I can save it. You can also add some attachments to the solution, for example, robotic program, and in the activity log, you can monitor the activity, the changes in your solution. Let's go to the selection of the robot. I'm going to use a Kawasaki robot, specifically RS007L. I can filtrate the robotic brands, so I'm going to choose Kawasaki, or I can search for my robotic model. So this is the one I'm going to use. I'm going to select it. On the side of the robot, we need to load the robot module, set of files containing functions for communication between the robot and the vision controller and execution of beam picking trajectories. We also provide several example programs for basic use cases. I have already loaded my robot module using the integration guide for Kawasaki. You can find all integration guides for all supported robotic brands in the documentation section. Okay, let's move on. Let's get back to the solution and go to the gripper. There are already some grippers defined. These are from the other solutions. I'm going to use another gripper, so I need to create it from scratch. So let's create a new one. It needs to have a name. And I need to provide a CAD file. So I'm going to click Browse and select the gripper STL. I'm going to hit Save, and right now the model is being uploaded and the volumetric model is being generated automatically. This volumetric model is used for collision checking. Let's check that the origin of the provided file is at the correct place, which is the base of the model, because here the real gripper will be attached to the robotic flange. Now we need to set up the tool point. I'm going to go to the tool point tab, and here you can use these arrows to select the tool point. I'm going to use the arrows to mark the approximate position of the tool point, but the best way to do this is to calibrate your TCP on the robot and put the values directly into the respective fields. I know the values for my gripper, so it should be 91 millimeters in y-axis and 254 for the z-axis. So this is the correct tool point as calibrated on the robotic controller. Now this is a magnetic gripper with a single magnet, and it does not matter how it is rotated when it grasps an object. From the tool point of view, it is symmetrical. To tell the system about the symmetry, I'm going to allow the rotation invariance. Automatically, the z-axis is chosen as the axis of symmetry, and it appears in the visualizer going through the tool point. I can limit the range of symmetry, but in my case, the tool point is fully invariant for rotation, so I'm going to leave it as it is. I can also choose the number of steps. The default is 8, and it is usually a good choice. You need to remember that with increasing number of invariances, there is more computations that need to be done, so the path planning will be slower. Let's preview my tool point invariances using the slider. You can see that the gripper rotates around the tool point. I'm satisfied with this, so I'm going to save it. And all that's left to do is to select this new gripper for my solution. Let's go to the picked object. I can define up to 4 picked objects to be used in a single solution. So let's add a new one. The process is very similar to the definition of gripper. We need to name the object. I'm going to simply put in object. I can provide a description of the object, for example, that this is a metal object. And I need to provide a CAD file. So I'm going to choose the correct one and save. Once again, the volumetric model used for collision checking is being generated. And in the visualizer, I'm going to check that this is the correct object. Yes, it is. This is the object I'm going to be picking today. Now we need to tell the system how the actual object will be picked. So we need to define some gripping points. You can define several gripping points for each object. Only with a good set of gripping points, the system will be able to calculate path for every object in any position and orientation. So let's create a new gripping point. As you can see, the tool point is automatically placed into the origin of the CAD file of the object. So I need to adjust its position a bit. Again, this is a very similar process to the definition of the tool point. I'm going to define the gripping point so it almost touches the surface of the object on its side. Okay. Now, we have 8 invariances on the tool point because it is invariant for rotation around its z-axis, which means we actually have 8 grasping combinations. But we can also consider this object invariant for rotation since it is basically a cylinder. Right now, I don't care about the holes on the side, so I will enable rotation invariance also for the gripping point. The axis is clearly not correct, so I'm going to select the y-axis. Okay, now it is correct. It is going through the origin of the CAD file of the object, and I can preview the grasping configurations, the invariances of the gripping point using the slider. I will again choose 8 steps, which is enough. Right now, I have a total of 8 times 8, so 64 grasping combinations. I guess I could grasp the object also from the bottom or the top, based on how you look at it. So I'm going to create another gripping point. Again, I'm going to adjust the position of the gripper. And this is the only place where the gripper can touch the object, so I'm going to save. I can choose a priority for my gripping points so that the system will prefer a specific gripping point during path plan calculation. I also have the option to disable a gripping point or a specific invariance, even a tool point invariance. This is especially helpful during teaching of placing positions for oriented placing. You see, the tool point invariance, the gripping point ID, and the gripping point invariance accurately define how the object was picked. These values are sent to the robot, and we can use them to teach placing positions. Once a combination has been taught, you can disable it so that the system will not use it anymore in order for you to teach the rest of them. There are a lot of combinations, but since the object is invariant, I do not care about the gripping point invariance at all. So I only need to teach a combination for each tool point invariance and a gripping point. And a skillful robotic programmer can use offsetting functions on the robot that will make the job even easier. Okay, that's all from the gripping points. Let's check the grasping method. Section grasping method does not have a check mark because there is always the default grasping method present. You can create several grasping methods if your application requires it. Let's check the default one. Grasping method is basically a blueprint for the beam picking trajectory. We are going to create several waypoints, and between these waypoints, the path planner will calculate the trajectories. Suitably defined waypoints will make path planning more successful and faster. There are 5 mandatory waypoints. Start and end waypoints are defined on the robotic controller and are sent to the vision controller at the beginning of beam picking. Between these 2 waypoints, every trajectory is unique and generated by the beam picking studio. Always try to define these waypoints above the center of the beam to keep the planned trajectories as short as possible. You can move the end waypoint towards the placing position a bit. The grasp waypoint is a gripping point or its invariance, so it depends on where the object is localized. Between the approach and the de-approach waypoints, all trajectories are always linear. These waypoints are placed relatively to the grasp waypoint and they maintain the orientation of the grasp waypoint. Let's check the individual waypoints. The start one, there's nothing much to do here, but in each waypoint we can define an action for the gripper to be executed. So in the start waypoint, I'm going to select the detach procedure, just to be sure that the gripper is in correct state, which in my case means that the gripper will be deactivated. The robot module loaded into the robotic controller contains empty functions for these procedures that need to be filled by the robotic programmer. Basically, you just need to set the correct digital output for the gripper. Let's save the waypoint and check the approach. As stated before, its position depends on the grasp waypoint. To approach the grasp waypoint from the direction of the used gripping point, we select option Found Gripping Point as the origin of the relative offset. The default distance is 100 mm, which is enough in my case, and of course it's in the direction of z-axis of the found gripping point. I could also select the robot as the origin of the relative offset, but that would mean that for the same offset values, 0, 0 and 100 mm, the gripper would be exactly 100 mm above the grasp waypoint in the approach waypoint. And I think that the path planning will be more successful if the object is approached from the direction of the used gripping point instead from the above. I don't want for the trajectory to be linear from the start to approach waypoint, so I'm not going to check plan linear trajectory. I will keep position tolerance to approximate option so that the trajectory can blend to the next one, and I won't select any procedure to be executed in this waypoint. Let's save and check the grasp waypoint. As you can see, the trajectory must be linear and I cannot change it. I also need to go precisely to the grasp waypoint, so I must use precise positioning. But I need to select the procedure for the gripper to pick the object, so the procedure in this case will be attach. Let's save the waypoint and go to the de-approach one. Once we grasp the object, we need to move away with it from the other objects. The best option is to go straight up. So for the de-approach waypoint, I will use the robot as the origin of relative offset. And I want to have the waypoint 150 mm above the grasp waypoint. So I will adjust the value. Other options of the origin of relative offset are the found gripping point I used for the approach waypoint, and then 3 more. The fixed plane option means that the waypoint will be always above the previous waypoint, in this case the grasp waypoint, and always in the same height from the robot base. This is very useful for deep bins. It doesn't matter whether the object is at the bottom or at the top of the bin, the de-approach waypoint will be always at the same height. Usually you will want it just above the bin. Then there is option to make the de-approach relative to the start or end waypoint. As I said earlier, these are defined on the robotic controller. I can use them to create a waypoint leaning towards one of these waypoints. Why? Because when I have an object localized near a wall of the bin and my start waypoint is defined about the center of the bin, I can create the de-approach waypoint in such a way that it will be leaning towards the start waypoint and away from the wall of the bin. That can be very helpful. Okay, for the other parameters, again, I must plan linear trajectory. I will leave the approximate positioning and I won't select any procedure for the gripper. Finally, let's check the end waypoint. And I will leave the end waypoint as it is. I do not need to change any parameter. That's it for the grasping method. And let's go to the vision system. Vision system binds together several things: a scanner with calibration, a picked object and its localization profile, then a grasping method, and some settings unique for each vision system. Let's create a new one. Vision system needs to have a name. I'm going to call it object detector. Each vision system has a unique ID through which the robot identifies it. In each solution, you can have up to 4 vision systems that can run in parallel. The robot can request a trajectory for the object from the first vision system, then a trajectory for the object from the second vision system, and so on. Next, I need to select a scanner for my vision system. I'm going to pick one from the drop-down. Then I need to choose the correct model of my scanner. This is scanner of size L. My scanner is mounted on the robotic cell. The other option is the robot flange, but my scanner is mounted stationary on the robotic cell. Then I need to select the picked object for this vision system and the grasping method. I have only one, so I'm going to use the basic grasping method. And now I can create the localization profile. Let's directly click Start Locate to see how the localization performs with the out-of-the-box settings. You can see that the localization found a lot of objects, but let's check the basic parameters. I'm going to leave the timeout on 10 seconds. I'm definitely going to increase the overlap from 15 to 50%, which sounds like a good value. And I'm going to define a bounding box just to be sure that no object is localized outside of the bin. This is especially helpful when you have multiple bins with objects and you only want to localize objects in a single bin. Let's click Start Locate to see how the localization result changes with the new settings. Okay, this looks pretty good. Let's save the configuration and quit the localization. Configuration of the vision system is almost completed. There are 2 settings unique for each vision system. The first one is gripper collision sensitivity. This parameter defines how much of the volume of the gripper can collide with the point cloud in the grasp waypoint. This value should of course be as low as possible, basically just to account for some noise in the point cloud that could not be filtrated or some light contact between the gripper and other objects around it. Then there is fast scan. Fast scan is a feature that helps improving the cycle time. How it works is that instead of the full 3D image of the scene, so the point cloud, only a 2-dimensional texture image is taken and compared with the one from the previous scan. Based on the fast scan settings, the system evaluates how much of the scene changed. Each point of the texture image is paired with the point of the point cloud. So when the part of the scene where an object was previously localized changed too much, the object is forgotten. It was either picked or removed. On the other hand, objects in the unchanged parts of the scene are localized much faster than during a full scan. Let's look at the parameters. There's full scan frequency, so only each, in this case, third scan will be full scan, the other 2 scans will be fast scans. But full scan will be also taken if less than 3 objects are found during the fast scan. Then these 2 parameters define how much the scene can change, and the last one says that if less than one object is ready for picking in the current run, the next scan will be full scan in order to localize more objects to have more candidates for path planning. Okay, I'm not going to use this feature right now. I'm going to finish configuration of my vision system by calibrating it. Let's go to the calibration page and start calibration. My scanner is stationary above the bin, so I'm going to perform the extrinsic calibration. For this type of calibration, the tool to be used is the calibration ball. The calibration ball is included in the Bin Picking Studio package. In my case, it is a snooker ball, so I'm going to choose it and click Proceed. While the calibration is starting, I will remove the bin to create space for calibration, because I want to calibrate in the volume of the bin. I will also rigidly attach the calibration ball behind the last joint, so on the gripper. I will let the robot take care of the calibration. I'm going to start the robotic program and wait for the calibration to complete. The robot module for each robotic brand includes a calibration procedure where you just need to reteach your robot calibration poses, and then it can be used anytime you need to perform the calibration. You can see that the robot moves between the poses and it requests adding of a new calibration point itself. Of course, I could also do this manually, but this is much faster once you prepare the program on the robot. We need to take at least 9 calibration points to have enough data for calibration. Once completed, the Bin Picking Studio tells me the accuracy of my calibration. I am also going to check the actual overlap of the point cloud with my robot model. This looks pretty good. The point cloud is overlapping with my robot model, so I'm going to finish and save the calibration. After successful calibration, all required steps of the solution configuration are completed. However, I have collision objects around my robot, so I'm going to go to the environment page to define them. That way, I can be sure the system will know about them and the robot won't collide with them. Currently, there's only the robot and the scanner on the scene. The scanner's position is based on the calibration. It is also a collision object, so the robot cannot touch it. Let's define a base for the robot. I'm going to draw a simple box. The name will be base, the type is environment, and I will place it a bit lower, just under the robot. Now let's define a bin. I have the exact model of my bin, so I'm going to upload an STL. The name will be simply bin. I need to select the CAD file, and the type is bin. Let's move it into the approximate position. Since my vision system is already calibrated, I can go to the Vision tab, connect to my scanner and trigger a scan. The point cloud in the visualizer will now help me to adjust the position of my collision objects. My robot base is a bit smaller, so I am going to resize it. And I will also move the bin so that it overlaps with the scan. Finally, just to be sure, I will define walls and the robot won't be able to move through them. I can simply put the robot and the bin inside another box object. I will call it walls, and this time I will choose virtual type so that it is transparent. Finally, let's resize it and place it into correct position. On the Robot tab, I can try jogging with the robot. To visualize the current workspace of the robot, I will click the Generate button. Path planning only needs to be done in the volume of the bin and around it. I should definitely define some join limits in order for the path planning to have an easier job. It will be faster and more successful. So I'm going to input some values. And hit save. I can once again visualize my new workspace. It looks good, it is much smaller, but the bin is still inside it. I can try jogging to confirm the robot can move freely around the bin. I am pretty satisfied with the result, which means I have a completed configuration of my bin picking solution. I am not going to change any parameters on the settings page. I will use defaults and go directly to deployment. At first, let's deploy the solution in the simulation mode. This way, I do not need to run the robotic program in order to call bin picking requests, but I can do it manually directly on the deployment page. When the solution is deployed, I can simply initialize my vision system with the start pose and the end pose. I can visualize them so that I'm sure they are correct. I want them just above the bin, and then I can send a scan request. You can see that immediately new objects are being localized and path planning is being done. We can inspect some objects. For example, the gold ones mean that the volume of the gripper in the grass waypoint exceeds the threshold for the collision checking, and the bright red means that inverse kinematics failed in this waypoint. All green ones are ready to be picked and we can visualize trajectories for them. You can even replay the trajectory. Okay, I'm satisfied, so let's stop the deployment in the simulation mode and start it again, but this time in the production mode and with the real robot. The robotic program I'm using is basically the example program included in the robot module. I just added a simple placing routine. So my robot will go above the bin, pick an object, and then go with the attached object back above the bin. From there, it will go to the placing position where a new scan is requested and the picked object is placed into another bin. Finally, the robot moves above the bin and a new cycle starts. Let's check it. Okay, you can see that the bin picking is running well, so that's all from my side. If you are interested in knowing more about Bin Picking Studio, you can attend our Advanced Bin Picking Studio training, where we can go into more detail. Until now, thank you for your attention and bye.